All right, we're going to look at the Get Started section of 3.2. Mr. Wheeler, you can press pause. The kids should be able to do this part for a couple minutes and then press play and we'll finish it up for them. Okay, welcome back. Let's take a look at a couple of these points. I'm not going to do every one. Point A, for example, if you were to reflect point A horizontally, that would be over the y-axis. So it's 1, 2, 3, 4 units. 1, 2, 3, 4 units. Right there is where it would fall. Make sure you know how to label that. That would be labeled as A prime. Okay, so that's what the horizontal reflection of A would look like. The vertical reflection always takes place over the x-axis. So instead of -4, +3, it'd be -4, -1, 2, 3. I'm pretty sure that you can see that right here. I'll just make it a little bit bigger. That's this point. And that point is a vertical reflection, and we would also call that A prime if that's the transformation we were attempting to make. Okay, so if you were to do that with points B, C, and D, you would get this solution. Now you can press pause to just make sure that everybody's got the correct points. The only thing they did differently is they called the horizontal reflection and the vertical reflection different. One was A prime, B prime, C prime, D prime. The other was A double, B double, C double, and D double prime. Okay. Okay, welcome back. Well, let's look at the construct for understanding. We're going to do maybe one, or for sure one or maybe two of these examples. So let's look at the first one. They're wanting us to take this graph and reflect it two different ways. So I'm going to copy this and put this on a fresh sheet of paper. So bear with me here. Okay, there we go. Why don't, while you're waiting for me to get ready here, why don't you graph this on your calculator so it could be a little bit more convincing. Okay, so this is y equals 2x plus 3. I'm going to move this over to the side here a bit. And we're going to play around with the name of this function a little bit. Instead of calling it y equals 2x plus 3, I'm going to call it f at x equals 2x plus 3. Okay, and you all know that y means the same as the function at x. All right, if we were to reflect this, let's reflect it horizontally first. Now, what would that look like? Let's draw a picture of that. If I reflect this horizontally over the y-axis, this red portion here would go to there. This red portion here would go to there, etc. So I got a couple of points there. -4, -5 would now become 4, -5. -2, -1 would now become +2, -1. And the graph seems to really fit that reflection. Okay, I'm going to put arrows on the end as that line, I assume, continues. Now just look at that graph. What is its new name? Well, its new name in y equals mx plus b form, I'm sure you all see that f of x is now equal to, whoops, let me type that better. F of x is equal to, now the slope is down 2 over 1, so it's -2x, and the y-intercept is still +3. Okay, if you think back earlier to our poster, we said that the rule for a horizontal reflection was f at input -x. Now, without drawing that graph, could I have used this mapping rule to obtain the name of that new function? Well, let's see. If you remember back to last year's course, Math 30 SIB, you learn how to replace x with this value in brackets. So the function at negative x would be negative x replacing what x used to be. So it would be 2 times, now x is being replaced with negative x, and then we'd add 3. So that mapping rule of f at negative x has led us to a new function called negative 2x plus 3. Now, is that what we got when we graphed it? Take a look. Definitely. Okay, so we now have a way to come up with a new function just by using a composite rule from last year. And as you can see, it fits. Let's now look at the vertical reflection. Okay, we'll do it the same way. We'll draw it and then we'll derive it. So the vertical reflection, if I was to reflect that graph over the x-axis, what would happen? Well, this part that occurs down below would go above, and this part that occurs above would go down below. So let's just check a few points. This point, negative 4, negative 5, would now be negative 4, positive 5. This point here of negative 2, negative 1 would become negative 2, positive 1. And this last point here of 1, 5 would become 1, negative 5. So that's what it would look like graphically. Let's derive it using our mapping rule. I'll just move this one to the side. Let's put it over here. So that's the horizontal. Get this out of the way. Are you paying attention? Proto, don't make me come over there. Okay, Brunage, pay attention, Brunage. Okay, what do we got here? What was I talking about? Okay, I was talking about this vertical reflection. So the mapping rule. The mapping rule for a vertical reflection is negative f at x. You check back to your poster and you can see that. Okay, so basically what we're doing is we're multiplying the function itself by negative 1. And what was the name of this function at the beginning? The name was 2x plus 3. That's what its name was. What is its new name after undergoing this change? Negative 1 times 2x would be negative 2x. Negative 1 times 3 would be minus 3. It now has a new name. What's its name? Its name is f at x equals negative 2x minus 3. Now let's just go back to the graph and see if we're convinced. Is the y-intercept over here negative 3? You bet it is. Take a look. I'm drawing a circle over that point. Is the slope down 2 over 1? Pick a couple points. Down 2 over 1. Down 2 over 1. Down 2 over 1. It definitely is. So now we have the name of that new function before having to even draw it. Okay, Mr. Wheeler, you can press pause now. Okay, welcome back. The next two graphs of the parabola and the cubic function, I'll deal with those next day when I come back. But I think we got enough to kind of go forward with. Go to the next page. The next page deals with this reflection rule, I believe, or is it? Let me just double check to make sure that's the right page. Okay, yes it is. So in conclusion, we could say that for a function f of x, the graph of y equals negative f of x is the image of the graph of f of x after a reflection in the x-axis. Okay, that's the blue graph. And also the graph of y equals f at negative x is the image of the graph f of x after reflection in the, you guessed it, y-axis. Okay, and there are the rules that we just spent some time talking about. And the image of the graph of f of x after reflection in the x and y-axis is always congruent. The graphs have the same general shape. Okay. All right, let's look at check for understanding number 1. I want you all to use a table of values, just like I did on a couple of examples last day, to map the new points. Okay, so you'll notice on my table I have picked all the bending points and end points. -3, 1, -1, -2, 3, -2, and 5, 2. Now, this graph wants us, question wants us to reflect this over the y-axis. So remember, the reflection over the y-axis is a horizontal reflection with a mapping rule of f at -x. Well, if you reflect a graph horizontally, what's going to change? What's going to change? Schmitty, what's going to change? Get your head in the game here, Schmitty. Okay, it's a horizontal reflection, so x changes sign. So x is going to change sign. So let's concentrate on the x values. So on my table, over here in my new table, a -3 becomes a +3, a -1, +1, +3, -3, +5, -5. Since it's a horizontal reflection, y doesn't change. It stays the same height as it was originally. So I'm just going to retype those exact same y values there. So this is a single transformation being a horizontal reflection. So I would like everybody to plot those points. And in a second here, I will reveal the solution. Okay, I'm waiting. Plot those points. Mr. Wheeler, you can press pause. Okay, welcome back. Here it comes. Did you get that graph? The blue graph is the newly transformed graph. I'll make it a little bit bigger for those people sitting in the wrong spot, maybe sitting at the back. Hannah, can you see that? Okay, and also the domain and ranges should be stated as well. Okay, let's go on to check for understanding number 2. All right, check for understanding number 2 wants us to perform a negative g of x rule. A negative g of x rule, if you look back to your poster, that's multiplying g of x by -1. That's a vertical reflection. What do vertical reflections do? Vertical reflections over the x-axis change the y values. We'll have to change our y values. So just be aware that these coordinates will change in terms of y. This graph is not as clear as to what its points represent, but as long as you're pretty close, notice that the y-axis goes up by increments of 2, so don't let that make your graph incorrect. So we have some coordinates. We have -1, -8. I've picked 0, 2. I picked 1, 1, 2, 4, 3, 2, and 4, 6. That's good to pick the bending points as well as any other x or y intercepts. Sometimes are good ones to have. So vertical reflection. The x values will stay the same. So I will just retype those in here. Okay, and over here the y values, as we said, change in sign. So -8 becomes +8, +2 becomes -2, +1, -1, +4, -4, positive 2, negative 2, and positive 6, negative 6. Okay, Mr. Wheeler, you can press pause and let's wait for everybody to draw a nice sketch. Okay, welcome back. Let's see how your graph turned out. Move this stuff to the side. And how does that look? This one has the blue graph being our newly transformed graph. Let's just double check some of the points that we came up with. We said that negative 1, 8 needs to be on there. That's right here. We said 0, negative 2. That's right here. 1, negative 1. 1, 1, negative 1. 1, negative 1. That's a bit off. 2, negative 4 seems okay. 3, negative 2 seems all right. And 4, negative 6 seems all right. Just double checking that 1, negative 1. 1, 1. Actually, that was supposed to be 1, 5. Okay, I got a mistake there. Okay, so let's change that. That's supposed to be on the original graph 1, 5. You guys probably noticed that before, but anyways, now it's 1, negative 5, and 1, negative 5 definitely works. Okay, you can press pause and carry on to example 3. All right, welcome back. Check for understanding number 3. This question gave us a graph of y equals 1 over negative 2x squared minus a half. And they told us that this graph was reflected in the x-axis, and its image is shown right here in red with the original graph. Okay, so it'd be interesting. Let's graph this on a calculator to see what exactly that function looks like. So that is 1 divided by, in brackets, negative 2x squared minus a half. Make sure you put brackets around that. Let's just take a look. Graph. Okay, so that definitely seems to make sense. It's graphed reflected over the x-axis, so that is a horizontal reflection. Oh, sorry, incorrect. That is a vertical reflection over the x-axis, and that definitely looks like the image that we have in front of us here. Okay, but the question was actually to find the equation of that newly formed image. So to do that, we need to take advantage of our mapping rule for that vertical reflection. That is a rule of negative 1 f of x. So we need to multiply this function by negative 1. So if we do that, you could write it like this, negative 1 times that function. And to simplify that function, we could just multiply the numerators together. Negative 1 times 1 is negative 1. And then a good algebraic strategy would be to simplify the negatives, because as we know, if we divide top and bottom by negative 1, it makes all the values positive. So this would be the equation of the newly formed image that we have in front of us. Okay, Mr. Wheeler, you can press pause and make sure that the kids have that written down.